Hello everyone, I'm Dr. Emilia Bertolo and I'm Principal Lecturer in Chemistry at Canterbury Christ Church University in the section of Natural and Applied Sciences. The aim of this series of videos is for you to become familiar with key concepts in atomic structure, electronic configuration and the periodic table. At the end of studying this topic, you will be able to explain some key concepts related to atomic structure. For example, what's an orbital, what are energy levels, and also the concepts of mass number, atomic number, and isotopes. You will also be able to use atomic number and mass number to determine the number of protons, electrons, and neutrons of a particular element. We will also be studying the periodic table, and you will be able to use the periodic table to extract particular information on an element, and you will also be able to use the periodic table to compare and predict the chemical characteristics of elements, their atomic size, their ionization energy, electronic affinity, and electronegativity. These videos are not aimed at chemists, so there will be many things that you probably already know if you have studied chemistry in the past. These videos are aimed specifically to those of you that in your degree are going to will need a sound knowledge of chemistry, but that they are not going to be your main career, your main degree. If you have any questions, please contact me at emilia.bertolo@canterbury.ac.uk. What is chemistry? Well, we can define chemistry as the study of the properties and behavior of matter. And matter is the physical material of the universe. Basically, anything that has a mass and occupies a space. So from an atom to a table to a tree, an animal, or a person. Properties are characteristics that allow us to recognize and distinguish one type of matter from another. And you can divide properties into groups. You can look at physical properties or you can look at chemical properties, and chemistry study both. So physical properties are the physical characteristics of the matter. For example, if it's a solid, a liquid, or a gas, its melting point, its boiling point. Chemical properties are things like flammability, how easy it is to ignite, how easy it is to react with oxygen. So chemical properties deal with chemical reactions. And all the matter that exists is actually due to the combination of a type of substance called elements. And those elements make up all the matter of the universe. We chemists try to understand the properties of matter in terms of the atoms that make up that matter. So an atom is a tiny building block of matter, and each element is a unique kind of atom, and we will talk a little bit later of how we distinguish one element from another. So for example, I've got here a compound called water, which is composed of 2 hydrogen atoms attached to one oxygen atom. The compound water is made of 2 types of elements, oxygen and hydrogen, 3 atoms, 2 atoms of hydrogen, 1 of oxygen. And those atoms joined together, is what we call molecules. So the properties of matter relate to the kind of atoms that make up that matter, the composition, and also the arrangement of those atoms, how they are linked together, and we call that the structure. So a whistle-stop journey through our understanding of the atoms. From very early age, philosophers have speculated about the nature of matter, what are things are made of. And it was in the 5th century before BC that Democritus came up with his theory of atomos. And he proposed this idea that matter, when break down to the minimum level, it was made of these atomos, and those were indivisible particles. They could not be cut any further. That got parked for quite a few centuries until in the 19th century, John Dalton postulates some of the things that we still use in chemistry for our everyday chemical life. He postulated that matter was composed of different elements, and elements were extremely small particles that he called, picking up Democritus' suggestion, atoms. So all the atoms for a particular element are identical to one another, and they have the same mass and they have the same properties. But the atoms of one element are different from the atoms of another element. And you cannot change the atoms of an element into another. You cannot convert a hydrogen into an oxygen or a fluorine into a sodium atom. So atoms are neither created nor destroyed in a chemical reaction. What we do in chemical reactions is we change the arrangement of those different elements, so and how they are in compounds. So compounds and form when you have several atoms of the same or more than one element combined, and in a chemical reaction you change how those elements are put together. And this does not hold for nuclear chemistry. We can now split the atom, but for your everyday chemistry, the chemistry we do in the lab, and the chemistry you're going to be working with to most of the time, these basic concepts still apply. The end of the 19th century and the beginning of the 20th century greatly improved our understanding of what atoms were and what they were made of. We did discover that actually atoms were not indivisible, that they could be divided, and they could be divided in electrons that were discovered in the very late 19th century, and protons that were discovered in 1919 by Rutherford and Chadwick, that in 1932 discovered neutrons. And in 1910, Rutherford also proposed this idea that most of the mass of an atom was actually condensed in the nucleus, and most of an atom was empty space. So how do we understand the atom nowadays? Well, atoms are made of subatomic particles, so we do know that, yes, you can actually split atoms. You can split them in electrons, protons, and neutrons. Electrons negatively charged and protons positively charged, and neutrons have a mass but they don't have charge. Protons and nucleus are in the protons and neutrons are in the nucleus, and the electrons are in an electronic cloud around the nucleus, and that's negatively charged. And the nucleus is very small and very dense, so 99.9% of the mass of an atom is concentrated in the nucleus, is due to the protons and the neutrons of that element. This is a typical example that is normally given to try to explain how much the mass of an atom is concentrated in a very, very small space, and how, despite the fact that atoms are really small, how there are quite a lot of empty space, because most of the mass is in the nucleus. So if you imagine a football stadium, and you imagine a marble right in the center of your football stadium, that marble will represent the nucleus of your atom. And in that tiny marble, you would have concentrated 99.9% of the mass of that atom. So nuclei are extremely small, but extremely dense. This is a table that's trying to show the properties of protons, neutrons, and electrons in terms of their mass and their charge. Well, we know protons are positively charged, neutrons are neutral, and electrons have a negative charge. With respect to the mass, you will see that both protons and neutrons are quite evenly matched. They're roughly the same mass in kilograms, tiny, but roughly the same mass. And if you compare that with electrons, you can see that they are several orders of magnitude smaller. So even if you have many electrons, you also have many protons. The protons are much larger, being tiny, they are much heavier than the electrons. And you also have in the second column the mass in something called atomic mass units. Because measuring masses of such tiny particles in kilograms or in grams, in any units that you can think of that we use to measure everyday things, is not very useful. 10 to the 27, that's not a very useful unit of mass. It's complicated to work with negative powers of 10 and, you know, that range, that tiny range. So chemists invented a different scale, something that we invented something called atomic mass unit. An atomic mass unit is that particular number, 1.66054, 10 to the 24 grams, so 10 to the minus 27 kilograms. And why that very strange number? Well, because it's 1/12 of the mass of an atom of carbon, and a specific carbon type of carbon, the most common one, which we call carbon-12. And I will mention what that 12 refers to in a later slide. So in that way, it's much easier, instead of using masses in kilograms, 1.67 10 to the minus 27, well, a proton weighs roughly 1.0073 atomic mass units. A neutron weighs again 1.0087 atomic mass units. Yes, electrons are still very tiny, and even with this invented scale, you still get a power of 10. But at least they are much more manageable in numbers. And the masses that we have in the periodic table, the masses that, if you have ever done any chemistry problems, you work, you know, the mass of hydrogen is 1, and oxygen 16, and sodium 23. Those are those atomic mass units. And in future videos, we will look at the way we have to weigh to bridge that difference between these atomic mass units, the easy masses that you get from the periodic table, that we get from the different atoms, and the masses that we can actually weigh in the lab, which are kilograms or grams or milligrams, to bridge those two scales, the one easy to do calculations with and the one that you can actually use in the lab. We use the concept of mole, and more about it in future videos. Atoms as a whole are electrically neutral. They are not positive, they are not negatively charged. Protons and electrons compensate each other. The number of protons in an atom, in an element, is the same as the number of electrons.